Imagine packing 155 kilowatts of computing power into a single server cabinet. I mean, that is enough to run an entire neighborhood.
Yeah, it is a staggering amount of power to put in one place.
In the second half of this year, we'll easily transition into the upgrade. So we have the Blackwell Ultra NVL72. It's 1.5 times more FLOPS. It's got a new instruction for attention. It's 1.5 times more memory. All that memory is useful for things like KV cache. It's 2 times more bandwidth, okay, for networking bandwidth. The next click, 1 year out, is named after an astronomer, and her grandkids are here.
Well, it really comes down to a fundamental bottleneck in how modern AI actually thinks. If you look at massive models right now, like DeepSeek V3, they use what's called a mixture of experts architecture.
Which is usually abbreviated to MOE.
Right, exactly, yeah. Instead of firing up the entire neural network to process every single word, the software only activates a highly specific subset of parameters. So it saves an unbelievable amount of raw compute, right? I mean, that makes me think of a massive restaurant kitchen with, say, 72 highly specialized chefs. You have one who only chops onions, another who only whisks sauces. But to get a single dish out the door, they have to instantly toss ingredients across the room to each other for every single order.
Yeah, that is a great way to look at it. And if they drop an ingredient, the whole kitchen just grinds to a halt. The bottleneck shifted from the cooking itself to the communication between the chefs.
Because the data is just constantly bouncing around.
Right, it's bouncing between different GPUs to find the right expert for a fraction of a second. So NVIDIA had to essentially knock down the physical walls between those chefs so they all share the exact same countertop.
Which brings us to the actual hardware. I mean, they crammed 72 Blackwell Ultra GPUs and 36 Grace CPUs into one unified rack.
Which is incredibly dense, by the way.
It is, but cramming chips together isn't exactly new. The actual breakthrough here, the reason everyone is losing their minds over this, is the 5th generation NVLink connecting them, right?
That is the secret sauce. This interconnect provides 130 terabytes per second of bandwidth. And because the data moves so impossibly fast, those 72 individual GPUs basically stop acting like a cluster of separate machines.
They just merge.
Exactly. For all intents and purposes, they merge into one single massive GPU. What's fascinating here is that the software doesn't even know it's talking to 72 different chips. It just sees one giant brain.
Wait, 72 of these GPUs acting as one in a single rack? I mean, a standard server rack would literally melt at a fraction of that load. I was looking at the Lenovo engineering guide, and pulling up to 155 kilowatts of power is insane.
It really is pushing the limits of physics.
So how does it survive? Lenovo must be doing something radical to keep this from turning into a puddle of expensive slag.
Yeah, they had to engineer a highly specific hybrid cooling architecture. I mean, you can't just blow cold air over this kind of density anymore. Lenovo designed a system that is 90% liquid-cooled and 10% air-cooled.
Oh, wow, 90% liquid.
Right. They integrate this intricate system of cold plates and manifolds directly into the compute trays. So the fluid is pumped intimately over the hottest components. And not just the GPUs and CPUs, but the high-speed NVLink switches themselves.
Catching the heat right at the source.
Exactly. Extracting the heat exactly where it's generated before it can even radiate into the room.
Okay, so they've managed to build a liquid-cooled superbrain that doesn't melt. But let's ground this for a second. When you look at the actual output, what is this achieving in the real world?
Well, during the pre-training of that mixture of experts model, this system hit 1,648 teraflops per GPU. To put that in perspective, a top-tier consumer gaming PC today might hit around 100 teraflops if you push it to the absolute limit.
That is just wild.
It is. We are talking about condensing an entire traditional data center's worth of power into a single rack. Overall, it delivers a 50x boost in AI factory output compared to previous architectures, and it generates real-time video like 30 times faster.
And we're already seeing this leave the lab, too. Cloud providers are racing to get this online. Like, Nebius just launched Europe's first live production deployment of the GB300 NVL72 in their Finland data center.
Which is a huge milestone for deployment at scale.
Definitely.
Yeah.
And if you're wondering why you should care about a supercomputer in Finland, it's because of what this scale unlocks for everyone. By making the training of these massive agentic AI models exponentially faster and cheaper, the barrier to entry just plummets.
Right. It completely changes the economics of AI research.
Exactly. We aren't just talking about snappier chatbots here. We're looking at accelerating breakthroughs in medical research and climate modeling that were frankly computationally impossible a year ago.
It forces us to rethink the boundaries of what researchers can even attempt to build. The future of AI is no longer just about etching smaller transistors onto a piece of silicon. It requires this intense, absolute co-design of hardware, software, and networking all working as one seamless entity.
So what does this all mean? The GB300 NVL72 proves we can successfully make 72 GPUs act as one single unit. But AI is scaling exponentially.
Which raises an important question to leave you with. If this is what it takes to network 72 chips, what happens when we inevitably need 7,200 GPUs to act as a single logical brain? How will the uncompromising physical limits of networking and power distribution shape the next generation of artificial intelligence?